the button. Oh, so we're waiting. Yeah, I'm seeing people joining there. Okay.
Okay, so good evening and welcome to this Swansea University webinar on sustainable batteries to support renewables and electric vehicles. My name is Paul Holber and I'm part of our recruitment and admissions team. And I'm joined by Dr. Jenny Baker, who will be presenting this talk. And it's going to be a really fascinating look into this really important topic. We'll launch a poll in a few moments once we're confident that everybody's here. And well, over to you, Jenny.
Okay, thank you, Paul. So yeah, I'd just like to sort of welcome you to this Swansea University seminar, where I'm going to talk about some of the work that we're doing on sustainable batteries to support renewables and electric vehicles. But before I sort of start that, I do just want to take you on a bit of a journey and give you some background into, you know, batteries and their uses going back through the ages really until we get to where we are now, because I think that gives us a flavour and idea of really where we're going with things. So Paul will just launch a little question and answer, so to see if you to understand what you guys know already about some of the history of batteries development. Is that up there now, Paul? You can see some questions. So there's how old is the oldest battery? If you can try and answer these quickly so that when I move on it will go through. So I think there should be 4 questions out there, I think. Are there 4? I'm just gonna get my slide to move on to next slide. So at Swansea, we're doing a lot of work looking at batteries and how they can support both the grid and electric vehicles. So we've got a couple of buildings on site, which you can actually give yourselves a virtual tour of. Paul will put again in the chat this link, which will take you on a tour through these buildings, and you can look and see lots of the technologies that we've got embedded into them, whether that's the photovoltaics on the roof, the batteries which are in both of the buildings, 2 different sorts, or some of the other technologies that we've got built into them. But also, so we've got batteries to support the grid, but we've also got batteries. We're testing a whole suite of different sorts of electric vehicles, and those will charge up from the batteries itself. So the batteries within the buildings, and also looking at from the PV that's on the roofs of these. Also, we're lucky to, not in Swansea yet, but both in Cardiff and Newport and also Carmarthen have electric buses. So it's not just a case of having to own your own electric vehicle. You can go on electric buses, and also electric bikes are a technology that are really moving forward and taking advantage of these new technologies and the new developments in battery technology. So I'm going to, in this next slide, give you the answer to the next quiz question, which is how old is the oldest known battery? So as far as we're aware, there was discovered something called a Baghdad battery, which was found almost found about 100 years ago, but has been dated back to almost 2000 years ago. And this was just a very simple copper iron type battery. So with a with an iron copper sheath and then an iron rod within it. And then if you added an acidic electrolyte, which may have been something like vinegar or lemon juice, it would give a small charge from it. And those of you who study in chemistry, you'll see that there's you know, both the oxidation and reduction reactions happening in that battery, just as you'll have been taught in chemistry lessons. But I want to move a bit further forward than that, because we've got to get all the way up to 2021 by the end of this talk. So back in 1837 was really the first moving, I wouldn't call it a vehicle, but a trolley. This was based on copper zinc, so it was a one-off type battery. But this was before even we first had Eunice Foote's work, where she'd done work. She was really the pioneer of understanding that carbon dioxide could increase the temperature of the Earth. So this was way back in 1856, where she investigated using very rudimentary experiments to see that if she had a glass chamber full of carbon dioxide, that warmed faster than a glass chamber full of air. And really that work then brought us to where we are now, where we really understand that emissions of carbon dioxide are going to significantly change our environment. So moving forward, there was then the invention of the lead acid battery. And this now is a rechargeable battery. So this really was a step change, where you can have an anode reaction where you've got lead reacting with sulfates and the reverse equation happening in order, so you've got a material that can be charged and discharged. And this battery then can be reused many times, and we're still using lead acid batteries in all petrol and diesel cars and some electric cars at the moment. So this technology, although over 150 years old, is still being used day to day. And these batteries also are fully recyclable. So we get about 99.9% of lead acid batteries are recycled. So although this is very old technology, it's still pertinent to what we're doing today. But I want to move forward a bit to see, so in 1880, well, skip through. So this technology really did revolutionize things. And back in 1895, you know, this very much does, you know, look like a car, albeit not quite a Tesla, but, you know, it was capable of driving people around and was very much ahead of the petrol cars at the time. And in 1899, so I'm hoping that third question's gone up. So this was called the bullet car. I believe he did squish down in there when he was going for the world record. But this then was actually capable of running, my mouse not bringing up the next one, over 100 kilometers an hour. So incredibly fast, you know, even now, I think, you know, 65 miles an hour. Oh, so we got 17% of you right on that. If I'd had the question in miles, you would have more of you been right. But yeah, it really was an incredible speed. The fact that it could go over 100 kilometers an hour, you know, not in the turn of last century, but the end of the century before that. So, so this is all running on lead acid batteries. And then the next slide, I don't know why my slides are not going forward. So no relation to me, but back in the States, again in the early 1900s, they were advertising electric vehicles as what every woman wants. And so that's a tagline. I don't know if the car companies today, is that my error there coming up on the screen? I've got a PowerPoint execution error. Can you see something, Paul?
I'm not seeing anything. It's all smooth as far as I can see.
My screen share has just stopped. Let me see if I can sorry about this. My whole PowerPoint has just crashed. Let's see if I can reopen that. So you want to, if you can be looking at the last question, which was, I think there was a question on there, which was what was the range of some of these electric vehicles? I don't know if that, what's the minimum age for riding a battery powered bike? Yes, okay, so I changed this one for our younger audience here. So let me just skip through. So I've got my slides up now. So yes, sorry, bringing back to where we were. So back in the 1900s, there was this electric vehicle that was
it's not sharing, Jenny, just in case.
Is that sharing
there
now?
We are. Yes, it is.
Yeah. Okay, sorry about that. So back in the 1900s, they were advertising electric vehicles that could travel 100 miles on a single charge. So this again is using lead acid batteries. And you might question, well why, you know, could we not do this 10 years ago then? And really, if you look at this vehicle, there's some clues in it. You know, it's very lightweight. It hasn't got all the bells and whistles that we demand these days. And also, you know, it wasn't capable of driving at 80 miles an hour on the motorway. So, but I think it also sort of shows that the technology can go so far, but sometimes, you know, you need to look at what utility you're asking of things. And, you know, do you need all of those bells and whistles? Could you have, you know, a more sustainable car without having all the add-ons that you've asked for it? So I'm going to, I'm finding when I don't know really what is happening with this. So petrol then dominated, and ironically, because of the lead acid batteries in it, the lead acid batteries allowed us to start electric petrol cars without having to get out the front and wind them up. And so this made petrol cars more convenient than they had been. So we had 60 years of domination of petrol, and then just before I was born, we had started with the 1970s, and we thought, we had the petrol crisis, and we'll go back to, you know, looking for electric cars and what can electric cars do now after all these 60 years of development. And we came up with this, which obviously shows that technology had not moved on before because there was no demand for it. So I think this is really is a link that, you know, engineers really can solve any problems that you throw at them, in my opinion. You know, I'm saying that as an engineer myself, but I think, you know, there needs to be a driver, and if nobody's demanding something from battery engineers or automotive engineers, then nothing will be done, and we will have something that arguably is not as good as some of those first vehicles that I showed you from the turn of the 1900s. Fortunately, this did prompt a lot of research happening, and some work that was recently awarded the Nobel Prize in chemistry in 2019, and it's work of 3 people, but they actually didn't all work on the same thing. So they didn't all do the same thing for this prize or work together. They were individuals who all did a step change. So we'll start with the guy in the middle, so Stanley Whittingham. He was the first person to really get a lithium-ion battery to work at all. So this had pure lithium, which is very, very reactive, and he got it to work, but it didn't really discharge very well, and had poor lifetime. So he won a third of a Nobel Prize for that. And then John B. Goodenough, who is still around and still doing battery research at the grand old age of late 90s, he developed a new material called lithium cobalt oxide for the cathode material. And because of this, he sort of solved the lifetime problem that the material could cycle. And so, you know, it lasted longer, but it still had pure lithium in and wasn't really a commercial product. And then the last person, so he got a third of a Nobel Prize for that. And the last person, Ikiro Yoshiono, he then really developed into what we see now as a lithium-ion battery that then really kicked off the consumer electronics from the 1980s onwards. And that then had a changed chemistry at both the anode and the cathode that not only allowed extra cycling, but meant that this whole system didn't have pure lithium in it, which was much less stable and less safe. So there were some really clever step changes in chemistry, but then there were also the step changes that sort of meant that this was something that, you know, we could use in a mobile phone or this laptop now that's not working for me. So that really made a big change. But while they were doing all that development in the lab and in the universities, the electric car were continued to be developed. And so the next sort of chemistry that we had was something called nickel cadmium, which this is a type of figure that we show that we're very concerned about in batteries for electric vehicles particularly, which is how many watt hours storage per kilogram. So how much energy can we pack into a certain mass? This doesn't matter as much for stationary storage because we're not having to move it around, but it's really important when you're trying to make electric vehicles, because if you're if this value is too low, then if you want to have a bigger range or it to go faster and you need more batteries on board, you're just making your whole system heavier. That then means it can't go as far. So to increase this watt hours per kilogram is very important. And you can see here that with the chemistry of developing nickel cadmium type batteries, this was sort of a 30% improvement. And we had, certainly in France, Peugeot were developing electric cars because they had nuclear power and they could sort of run these quite easily. They had some stayed on the road a very long time. So this is one sort of showing 1.5, is that right? 150,000 kilometers it will be. So that they had good lifetimes, but they didn't necessarily go so fast and have such long range. Then moving on, we then had the nickel metal hydrides, which again have another step change improvement in this energy density. And this was used predominantly by Toyota and in their hybrid electric vehicles. So they still had a petrol engine in them and they're still emitting fossil fuels, but they could make a petrol engine slightly more efficient. These are now being marketed as chargeless hybrids, the self-charging hybrids. But the reality of them is that, you know, you can't get energy out of nowhere. And so these cars are just basically more efficient petrol cars. And, you know, so when they say self-charging, they just mean it's a more efficient petrol car there by use of this battery. So then the next step really is when those lithium-ion batteries, so way back in the 70s and 80s, when all the research was happening in the universities, we've now come, it's taken almost 30 years to get it into a vehicle. And it is that sort of lifetime to bring these technologies forward to maturity. And initially when we had lithium-ion batteries, they were only at 100, so 100 watt hours per kilogram, only a slight improvement on your nickel metal hydrides. But now, as it's become a much more mature technology and sort of lots of small changes have actually managed to make it 2.5 times as energy dense. And this really, I feel, is the sort of first electric car that could sort of replace petrol cars. You know, at least the last one to compete against petrol cars, I think, was back in the early 1900s. And so it's taken almost 100 years to then bring on a new electric car that can compete with petrol, which was the Nissan Leaf. And then what I'm going to just take you through, and then we then got Tesla, which also came on the market at that time. And really, I see 2011 is really when electric vehicles, you know, started to come of age. And Tesla, basically their batteries are very similar to, you know, if you've got an AA battery at home, these are slightly larger than AA batteries. You can see slightly larger diameters, slightly bigger, but in practice are the same. And these just have, so the battery is just a rolled up anode and cathode, and rolled up to make this cylindrical cell. And then to make your car battery or your bike battery or your bus battery. You just have more of these until you've got in as much capacity as you want. So it's quite a simple system and quite a modular system, because you can just keep adding and have the design that you want for these vehicles. And I think that's really benefited Tesla. And then you're making millions of these, and then you start getting the economies of scale and the economies from your factory sort of setup of this. So obviously, we're talking about climate change and how come using electric vehicles and batteries, how is it supporting the drive to net zero? And there's certainly been a huge number of press releases saying they're not any better, they're no more climate friendly than ordinary cars, and are they even worse? Now, I just picked a few of these. There's been a huge amount of research done in this area to look at it. And one thing, so in fact, I think I sent it to Heather, another link, but there's been a lot of work really understanding this, and where do these headlines come from if they're not true? I think that's one question that I think people might have. If you look at how much energy was needed to make some of the first batteries, that was a lot more than how much energy we need now, because we've made huge strides in the manufacturing and the chemistries and how efficient we are at using our materials. Also, the fact that the electricity that we're charging them up from is getting has less and less fossil fuels in it over time. But even if you had a coal-fired power station that is making electricity that you put into your electric car, over the full life cycle, that will be more efficient than a petrol car, and will produce less greenhouse gas emissions than a petrol car. So electric cars aren't the be-all and end-all, and I'll show you some slides at the end to sort of confirm that, but they are better than petrol cars without a question. And I'll just run you through some of the things that we do to sort of understand and model this, because we do something called a life cycle assessment, where we look at all the impacts of making anything. So not just what's the global warming potential, or, so we call this CO2 equivalent. So mainly we look at carbon dioxide emissions, but there are other greenhouse gases that also cause global warming. So we wrap them all up to this one feature. And then there are many other things that we look at when we look at an environmental assessment, because we don't just want to worry about, climate change and then find we're polluting our oceans, or that we're, making humans ill by using toxic chemicals. So we have all of these different environmental impacts that we look at. So ozone depletion, so over the poles there's an ozone layer, and that could get damaged by certain chemicals. So we look at all of these things. I'm not going to go into all of them now, because that would be a whole module probably at undergraduate level, but we do consider all of these, and there's just two that really I think are very pertinent to this, which is firstly global warming potential. So how much carbon dioxide emissions are we creating through making the battery and using the vehicle, and then also material resource scarcity. So this is a feature of how much material do we need in order to do this, make this thing. And that's something that does go up with the use of renewable energy. So we really need to look at, which materials are we mining and how can we recover them and use them most sensibly. And then we do something called a cradle to cradle assessment. So we take the materials that we need to make our battery. And then you'll see this arrow is getting smaller at each stage, because then when we make our battery, we get some, that came last. So some of the batteries might be rejected, so they go to battery disposal straight away. So we extract materials, so this is mining. We then, collect our materials and refine them and send them to the factory to then make them into batteries. Some of them may be rejected if the factory is not very good, or it's got a new product, or something went wrong. Most of those materials hopefully go into a battery that you'll use. As you're using it, you use electricity in and out, and those may not be the same size. So the battery use stage, the battery's not 100% efficient. It may be 90–95% efficient. So we do need to take into account that some of that stored electricity just got lost during the battery operation. Then we need to look at how we're going to dispose of it. And there's sort of 3 ways to dispose of it. One is throw it away into landfill. Now in the UK, we've got a lot of legislation, in fact, some European legislation. So this doesn't happen with batteries. Now, obviously, some people will put a small coin cell or whatever in the bin. I can absolutely guarantee you that that is not happening with electric vehicle batteries or with vehicles for the grid. Most notably because they're so large and they've got so many valuable materials in them. So if you did throw them in landfill, somebody would grab them out and sell them on eBay. So, you know, that although is often expressed as a concern, isn't really something, you know, we really need to be worried about there. But what we do need to look at is when we do recycle those materials, are they all going back into here so they can be materials to make a new battery? Or are they going here, which is downgraded materials? And that's really the biggest concern at the moment, not landfill, but that maybe they get used for a less good application that means that the whole value of the material is not realised. And we've just got funding at Swansea to look at, for some more research to look at how we can make sure that when we recycle batteries, we can really make sure that the materials stay clean and stay engineered in a way we can put them back into batteries. For those of you who may want to know more and get some sort of stats and figures on, you know, battery emissions and whether they really are better than petrol cars, I really recommend this paper, and there's a link in this here to that. I don't know if you've got a way to share that, Paul. I probably should have sent that before, but it's in Joule, and it's called The Underestimated Potential of Battery Electric Vehicles to Reduce Emissions. One of the other things that we're looking at is, you know, can batteries be used, one, to only charge when the grid has got spare capacity, so at night time, and also could electric vehicles also be used in a 2-way system, something called vehicle to grid. So where if there's really a big shortage in the power supply, or maybe we've got a big upturn, it's been a big football match and everybody's turned on their kettles and using more water than normal, that causes a big draw on the grid, could that be supplied by our vehicles? So there's a lot of potential in electric vehicles to actually make things more sustainable if we can use them properly. So this periodic table, so again, if any of you studied chemistry at GCSE or A level, you'll be familiar with the periodic table, but probably doesn't look quite like this. So what this table looks like, you can see that the shapes of these, or the sizes of them, is due to how much there is available within the Earth. So silicon's quite big, we've got a lot of silicon, oxygen is quite big, and some of the other materials are quite small. Here you can see cobalt and nickel here, which are 2 components used in some electric vehicle batteries, and they're quite small. And also then the colours are whether there's a risk to supply or not. So the green are the ones that we're trying to really work on and use in our batteries. But what you can see here is that, let's see if these, so at the moment, the current electric vehicles tend to have lithium, carbon. So carbon is green, there's plenty of carbon, but there's not always carbon in the form that we need it. So some of the specialist types of carbon for battery materials are very rare. So graphite flakes is a critical raw material. So that means that we're worried about how much there is, and we want to make sure we've got good supply chains for it. And here you can see cobalt, nickel and copper all again of concern. There's a rising threat from increased use. And if you look at these little white symbols or black symbols, this little symbol here, these are the chemical elements that are used in smartphones. So you can see there's quite a lot of similarity with them and batteries. So these are really, we're trying to look at particularly the red and orange elements that, you know, how can we make sure either we don't use them, or if we do use them, we can really recycle them well. So I'm just going to go through a couple of lithium-ion chemistries with you, because there's actually not just one sort of lithium-ion chemistry. So one common lithium-ion chemistry is called lithium nickel manganese cobalt, or NMC for short. And you might see this written as NMC 111. That's a sort of old version where it had the same amount of nickel, manganese and cobalt. Sometimes you will see them, so the new chemistries coming through are something like 811. So that means it's got 8 nickel to 1 manganese and 1 cobalt. And so that's beneficial, because what we're finding is there's a real big problem mining cobalt, and there's only a few places in the world that you can mine it. And as you can see, none in the UK. The Congo here is the main source. Many companies commit not to buying cobalt from the Congo because of their use of child labour, but then that means that they're limited to very small areas in Morocco here, some in Australia, in order to get their cobalt, and so it's becoming more scarce. And so for that reason, one, they're looking to remove the cobalt from these chemistries, so as I say, going to a similar chemistry but just with less cobalt in, or moving to a new sort of, well, actually it's an older sort of chemistry called something called lithium ion phosphate. So this now has no nickel and no cobalt in. I don't know why they, let me just see. Yes. So then the nickel and the cobalt's been replaced by this stuff, which is iron phosphate. So if any of you or your parents are gardeners, this actually can be made into slug pellets. So it's fairly common material, not particularly expensive. So we've still got lithium in there, but the phosphate is much cheaper. And what you can see here, so these diagrams here, these sort of spider web diagrams, are quite useful in comparing different materials. So what we've got here is the NMC, which I showed you before, which is used in a lot of electric vehicles. And you can see it's higher cost, and it's not as safe and doesn't have as good lifetime compared to the LFP. But the LFP chemistry, so the lithium iron phosphate, I was talking about the energy, the specific energy. So how much energy can we store per kilogram? And here it's much lower than the NMC. So that's the disadvantage of it. But despite that, it still is being used in certain electric vehicles, and particularly in electric buses, where maybe the performance is less important. And then there's actually a whole host of different, I won't go through these, but you know, many different lithium ion chemistries. And what I think we'll find over the next few years is that people will tailor these, different car manufacturers and different vehicle manufacturers will tailor these for different applications. So there's some that will charge much more quickly. So this NCA material will charge really fast. So there might be some premium cars that want really super fast charging. Others might be more bothered by safety or you know, cost issues. So there'll really be a bit of a balance, and I don't think all vehicles will have the same lithium ion chemistries within them. They will develop depending on what people want and need. So to just now move sort of how are we looking beyond this? So we've made some really good improvements. I think lithium ion batteries are very mature technology now. If you're buying a lithium ion battery, whether it's in your bus or your bike or your car, you can be pretty certain it's going to meet what the manufacturer's committed to. This is very well-known technology, but it's got lithium, and lithium demands, I think, is going to be an issue moving forward. there's probably enough lithium in the world to do what we need to do, but the issues are, you know, how much energy is it going to take to mine it? The first lithium that we take to mine, and we take it from the easy places, and then as we've used all that up, we need to go to places where it's more embedded in ores and takes more energy to get it out. So we need to start looking at other materials, and that's really where we want to look at sodium-ion batteries, and this is research going on in Swansea. So sodium, very, very abundant, the fourth most abundant on Earth by mass, but also, you know, salt water. We're surrounded by it here. It's very easy to extract. And then that tends to be coupled by something it needs. So you've got sodium, but you also need some other materials in there. And what we tend to work with in our lab is something called Prussian blue, which this was a pigment back in the times when all those electric vehicles that you saw at the beginning of the talk, a paint pigment, Prussian blue was a very common one. And so again, these are all abundant materials, carbon, nitrogen and iron. So here you're getting then a battery, and in fact there's no copper in this as well. So really you're looking at nice abundant materials, aluminium, sodium, copper, carbon, nitrogen and iron. And the positive thing about that is that those materials are available, you know, in every country in the world. So there won't be sort of the political issues with, you know, will that country sell me the materials that I need to make my battery? So this is really a big advantage. At the moment, it hasn't got the same energy density as lithium. So some of the first uses may be for stationary energy storage, although people in India are already starting to use this in public transport, in buses, because they don't have any lithium sources themselves. So it won't be for the high performance applications, but it really is a great way to sort of save the lithium and save those precious elements for the applications that really need them most. And then, so here is just some photos from in our lab. So when we're making the batteries, the liquid-based ones, we need to work in a glove box. So this is an argon environment inside here. So obviously people couldn't work inside here. So we stick our arms in the gloves and do our experiments within there. We've also got all sorts of characterization technologies so that we can understand how these materials are working. And then this new bit of kit here, which is a near-infrared sintering device, which is a way of very quickly heating materials with lower energy demands than conventional ovens. So this is another way where we're trying to make the manufacturing process more sustainable. And then I just want to finish up on a couple of slides from my PhD student. So she is looking at solid-state sodium-ion batteries. So this is where they've got really great potential to have much higher performance if we can get them to work. So at the moment, the issue with getting them to work is how we get the solid state electrolyte, which is this material here that Becky's looking at how to form, and how you keep it in contact with the carbon anode on one side and the sodium Prussian blue on the other side. So she's working on, you know, how can we manufacture these? It's the manufacturing that's difficult, to manufacture them and get the high properties that they've got potential to have. So this is one of her pellets that she's made. So she's pressed this powder into this sort of pellet form, and the material is a very sort of complex chemistry here, which is actually called nasicon for short. So it's sodium superionic conductor. So it's a solid ceramic, so it will hopefully be very stable when it's working, but that can conduct electricity. So this isn't your normal ceramic mug like you've got here that doesn't conduct electricity. This will, well, it's got ionic conductivity, so it will conduct ions through it. And then, so I just want to sort of finish on, so she's got a ceramic material she needs to sinter at very high temperatures. And so we're actually getting this machine installed next week. Hopefully that should be a video if I can press play. Let's see, play on it. Okay, we'll have to skip that one, and on a dud note, sorry about that. But it was really just showing this machine will heat this steel to red hot in 30 seconds, sorry, not 30 seconds, 10 seconds. So it can really achieve very high temperatures very quickly. And what we're hoping is that will reduce the energy input, because usually we need to sinter this material at 1200 degrees for 24 hours, which obviously requires a lot of energy and a lot of time. So that's something that we're looking at to move that forward. And yeah, so the last slide really to sort of sum up on sustainable transport, you know, when we talk about electric vehicles, you know, we tend to personalize it. So we bring it down to personal cars but actually when you look at how many are being used, and what I'll just put here, sorry, is that we've got 2- and 3-wheelers, and this isn't including electric bikes, but like mopeds and tuk-tuks and those sorts of things. We sold over 250 million of these sorts of 3-wheelers. So this then compares to passenger vehicles, which are about 30 million. So we're nearly 10 times as many of these sorts of vehicles on the road. And these are really very efficient vehicles, because so what you can see per person, if you have an electric vehicle, your battery size needs to be, the smallest ones have 24 kilowatt hours. Some of the bigger SUVs might even have 100 kilowatt hours of battery just for your own vehicle. If you use a bus, that comes down to, so the bus is sort of the premier here in terms of sustainability, between 0.1 and 1 kilowatt hour per person traveling on that bus. So much more efficient in terms of battery usage. And the electric vehicles, the 2- or 3-wheelers are somewhere in between, but again, much nearer the bus than they are these huge numbers required for personal electric cars. And so, you know, this market sector is going to make a huge difference and won't require so many resources. Whereas if we go down the line where always we just continue as we are as single person cars, then we're going to need a huge number more batteries. So really, this isn't just a technical problem now, this is a policy problem of how do we incentivize people to move to these more sustainable electric vehicles than just, you know, replacing an SUV petrol with an SUV battery. That's not really going to solve all the problems that we've got. So yeah, I'll just sort of summarize here, you know, bus, train, EV, car share. Then if you must buy an electric vehicle, your own personal electric car, go for the smallest battery possible, the most efficient. So some of them do more miles per kilowatt hour than other ones, particularly the smaller, lighter ones, again, tend to be more efficient. And then finally, this is sort of less important, but try to go for one, you know, without nickel or cobalt in it, because those will be, and again, this is like go for the cheapest car possible as well. So that's really how you get the most sustainable method of traveling by an electric vehicle, I guess. And yeah, as a last slide, you know, we then need to recycle these batteries. At the moment, there are very little electric vehicle batteries to recycle because they last 10 to 15 years. And also, if any get liberated from the vehicles, so say there's a car crash or something like that, those vehicles often go straight away to a second life, either in a stationary application, or there's a number of companies now who are retrofitting petrol cars with electric motors and batteries. So, but we have been awarded from the government to investigate recycling batteries and second life, and we've already got undergraduate projects working in this area. So this is an area I see like Swansea is going to develop further over the next few years, alongside our research in sustainable battery materials. So that's all I'd say. So thank you for listening. And if you've got any questions, let me know.
There was, Jenny, there was one question that went into the chat here that says, could an EV use multiple battery types to give the benefits of all of them?
That's a really, really good question. And I'd say, yes, sometimes that is something that's being looked at. And not just battery types, but supercapacitors. So if you've understood, so a capacitor basically gives a really high amount of power, but it can't store much energy. So it will give you, if you want to put your foot down very quickly, you can get that from a supercapacitor, but you wouldn't be able to stay in it for very long. And so hybrid battery supercapacitor vehicles are coming along. And in fact, one place they've been looked at is in buses, with the idea that when the bus stops at a bus stop, if it could charge really quickly using the supercapacitor and then discharge that into the battery. So at the bus stop, it charges just a small amount, but really, really quickly. Then that could also be a way of keeping the bus topped up with charge without it needing to sort of stop and charge at the end of the route. So yeah, really insightful question there, and the answer is yes, and we need more people thinking like that. So yeah, thank you for that, Anna. And then I think there's
one above that it's
yes.
It's more of a comment. Well, if you'd like to address it though, can you see it?
Yeah, so yeah, I can see that one. So it's a question that the waste battery of electric vehicle will be problematic compared to using hydrogen as a fuel. So what I'd say is that a hydrogen vehicle also needs to have a battery in it. So there's still going to be the issue of batteries at end of life. And I think at the moment, the issue of batteries at end of life, you know, is something that we haven't completely solved now, but certainly by the time that those batteries reach their end of life, you know, there's an awful lot of funding and drive to be ready for that waste stream. And I think we won't even call it a waste stream, you know, it will be a resource stream that we will not want to be shipping those waste batteries to another country. You know, if we've purchased those batteries and bought all those expensive elements, we don't want to then ship them for somebody else to get the benefit of them. And I think most countries are seeing this as an opportunity, not as a problem to solve, but as an opportunity to gain access to these minerals and these elements, even if they can't mine them, you know, in their own countries. So if we use the energy store method, I'm not quite, I don't quite understand that question. Avijit, would you like to come on the chat? Could you, yeah, if you'd like to sort of ask that question live, if you wouldn't mind, or put it a different way in the chat. Hi, yes, do you want to speak?
Good evening, ma'am. I'm grateful to attend such astonishing event. My question is like that: if we use photovoltaic cell with that, and after that we use such energy store method that we collect energy from the sunbeams, and after that, after calculating some amount of energy what we required after a certain time, and after that we could use that energy like that. My question is like that, like using photovoltaic solar cell or like that.
Exactly. So yes, we are doing a lot of work in that area. So the buildings that we were, I don't know if I can click on that, it's not, but the building that we are working on in, so can you if I do this as a new share. So here, this building, I'll need to now try and step out of it now so you can see from the outside. So these buildings all have photovoltaics on the roof of them. Oops, sorry, I'm going around now. I'm not very good at navigating this. I feel like, so what we then have is a live dashboard here where, I want to just remove that. So you can actually see it. So we've got photovoltaics on the roof, and then we then can either directly charge electric vehicles with it. We can directly use it, you know, for people's computers or for heating, or we can store it in batteries. So yes, definitely, we're looking to use renewable energies to store. And in the UK, we're really quite ahead in this area. I would say we're sort of, well, we're not world leading. I'd say Portugal and Costa Rica are world leading in renewable energy, but we're up to about 17 or 18% wind power on our electricity grid in the UK. Similar sort nuclear, so in terms of low carbon, and about 5% solar, because we're not as sunny as some places. We're doing some research with a number of universities in India, and some of those buildings can get 2 or 3 times the amount of energy from their solar panels as we would in Wales, because you know the weather's slightly different, but we still can find that the solar panels are very effective. So yes, I agree, it's much better if we use renewable energy to charge all of these batteries.
Thank you, ma'am. Thank you.
Is that it? Any other questions? I'll just go through. I don't know if I can share the results of the, I don't know, can you see all the questions on the poll? I was just going to go through. So did they show whether they were correct or not, if people know? So I think the minimum age for riding a battery powered bike on the road in the UK. So most people thought it was 10. My son would love that. He's 10 and he'd love to be able to ride my bike legally. Unfortunately, it's 14. But I think maybe we should put the results of these polls to maybe the Welsh government and say, you know, we think there's a demand for it to be. In fact, 60% of you think a 10-year-old would be able to, because either there isn't one or it's or 40% of you think 10. So I think that's a really good result, even though it's wrong. So, because yeah, I think that would really benefit and help get a lot more kids to cycle to school, especially if you live in a hilly place. So, but I can't see the other questions.
They were all done as separate polls. So if you, I think if you click, you have to click back into the
poll.
Close it, and if do you want me to? I can look.
I think that's all right for now, unless.
Here we go. If I go back to the first one, there we are. Yeah. Can you see that now?
Ah, no, I've now got it. So how old's the oldest battery? So nobody's thought it's 100 years old. Well done. And 2000, so 30% of you were right. But I think that was a very hard one. When I put that poll up, Heather asked me if I'd actually got the wrong answer because she didn't believe it was 2000 years old. So when was the first electric car made? Brilliant. 83% of you got that right. You did better than the Institute of Materials people, who I think only 12% of them got that right when they did that. So well done. Top speed, 17%. I think that was very similar to the Institute of Materials. So, and I think that was. And then what was it?
That was all of them, yes.
I didn't give them that question, so that's a new one for this thing. So, well, is it? So that looks like no further questions.
I don't think so. I did find the Joule article and share it in the chat,
Okay,
Jenny, as well. So.
thank you.
Okay,
Excellent.
well, thank you to everybody who's come along. If you do have any questions, if you think of something later on and want to get in touch, we're always, I think Jenny was sharing her, was that your Twitter handle earlier on?
That was my Twitter, but I mean, feel free to sort of forward on. So I'm actually an admissions tutor for mechanical engineering MSc, but you know, I'm happy to take questions for undergraduate, you know, questions as well, or you know, forward them to people who'd be appropriate. So
I've just shared my email address in the chat. So my email address is p.d.holborough@swansea.ac.uk, and feel free to get in touch with me with any questions, and I can forward those on to Jenny for you.
yeah, okay, yeah, thank you. Yeah, no, I'm more than happy to, you know, answer anything, and we do a number of last year we had some, you know, A-level students who were able to come in and do placements. Occasionally we have opportunities for those sorts of things. So yeah, keep an eye out and keep in touch if there's anything that sort of interests you on that side.
Wonderful. So thank you so much. Thank you, Jenny. And I guess that's pretty much almost exactly an hour, isn't it? 56 minutes. So
yeah.
Thanks to everybody for staying with us, and we do hope to see you here in Swansea.
Excellent. Thanks, guys. I'll stop there.